This involves the Riemann sum definition of double integral. So we have an infinite sum over here, and this was proposed by Ovidiu Furdui of Romania in a School Science and Maths journal. First of all, let's review the idea of Riemann sum. First of all, for 1D and then for 2D. Okay. So let's say in 1D, our integral from a to b of f of x dx is there. We know that this is actually an infinite sum, and its corresponding Riemann sum will be basically sum going from I equals to 1 to n, and then f of a plus b minus a by n times I, b minus a by n, and this is equal to the integral when n goes to infinity. So basically over here, this is our delta x, and this is a plus delta x times I, so this is our xi. And when n goes to infinity, basically the delta x goes to 0. Yeah. So limit delta x goes to 0 also is equivalent. Now in 2D, how do we deal in 2D? So basically if we have 2D, where x is going from a to b, y is going from c to d, yeah, we now need two different parameters. Like for every x value, there's some y value going on. Yeah, basically we have function of x and y. Let me show you. I will show you the definition, and then it will be clear. This is for y, this is for x. Okay. Now again, how I will write is sum from I equals to 1 to n, sum from j equals to 1 to n, and then what I can write is basically f of a plus b minus a by n times I, c plus d minus a by n times j. Yeah. And now we need b minus a by n, and then d minus c by n, and limit n goes to infinity. Now let me explain. Yeah. So basically over here, this is our xi, this is our basically yj, yeah, and this is our delta x, this is our delta y, so correspondingly this is our delta a, and as n goes to infinity, our delta a will go to 0 over here, delta a goes to 0. Yeah. So basically now we have a double sum. Yeah, and in the double sum, what we basically have is basically for every xi, like yj will go from 1 to n, and n is going to infinity. So basically, we have a sum like this, and this is also like analogous to our original 1D definition. And yeah, now with this we are ready to begin. Okay. So now let's see how we can manipulate our problem into a similar expression where we can use the Riemann sum definition. Yeah. So basically we have limit n tends to infinity of 1 by n. Let me erase this because this isn't looking good. It is infinity of 1 by n, sum from I equals to 1 to n, sum from j equals to 1 to n. Yeah. And now, okay, so let me remove this 1 by n, and basically let me put it 1 by n square over here. And then here also I can keep 1 by n plus j by n, and also over here I square by n square. Yeah. So basically, because I took a n from denominator common, now I can write this as 1 and j square by n square. Yeah. So basically, now let's say, now in this form, let's say if our a is 0, b is 1, c is 0, d is 1, and f of x comma y is just x plus y by x square plus y square. Now for these, in this setting, our this definition exactly matches the expression over here. Can you check that? Yeah. For this case, our sum exactly goes to this expression over here. So that's why now we can write this expression as integral from a to b, 0 to 1, integral from 0 to 1 of f of x comma y, and then dy dx. Yeah. So now after this step, it's easier to go because we know the f of x, y. So integral from 0 to 1, integral from 0 to 1, x plus y by x square plus y square. Now it's not a great trouble to solve this expression, basically. Yeah. Now to solve this, we can first note that I can break this into two integrals, okay? To 1 x by x square plus y square plus integral from 0 to 1, integral from 0 to 1, y by x square plus y square, and also over here it's dy dx, over here that's dy dx. Yeah. And now that our x and y are just dummy variables, we can just I can just write over here x and then y square plus x square as well. So that's the same, yeah. So that's why we can write this as 2 times integral, because these are essentially the same integrals. Yeah, can you see that? Because x also going from 0 to 1, y also going from 0 to 1. Yeah, and basically, even if we interchange x and y, there's no difference. Yeah, basically, that's why I can write this as 2 times 0 to 1, integral from 0 to 1, x by x square plus y square, now dx dy. Now after this, what can we do? Okay, so I can basically write this as integral from 0 to 1, integral from 0 to 1, or 2x by x square plus y square. And now in the numerator, we have derivative of denominator. Yeah. So that's why 0 to 1 ln of x square plus y square from 0 to 1 dy. Now this is an easy thing, I guess. 0 to 1 ln of 1 plus x square minus 2 ln of y. Now we can integrate this on your own. Ln of 1 plus x square times x minus integral of 1 by 1 plus x square times 2x times x dx. Okay, and this over here is minus 2 times. You know that integral of ln y is y ln y minus y. But wait, and this is also y, not x. I'm sorry. Okay, no, fine. Y ln y minus y. Yeah, this is a standard integral. Now for this thing, here we can write this as, I can take 2 outside. I can take 2 outside and write this as we had y square, so y square plus 1 minus 1, yeah. That gives me y ln of 1 plus, what is this here? Now fine. 1 plus y square minus, that is 2y plus 2 tan inverse y. Why is it getting so bad? Okay, 2 tan inverse y minus 2y ln y plus 2y. This from 0 to 1. Now try to evaluate this. Yeah, you might need to use limits, because here we will have okay, over here I guess. Here you might have 0 times infinity, so you might want to use limits. Yeah, or else there's really no problem. Let me do it again myself. 1 ln of 2 minus 2 plus, this is pi by 2. Now this is 0 plus 2, now minus 0 minus 0, sorry, plus 0 minus 0. This is also 0, you can use limits, plus 0 plus 0. So you can see that this is pi by 2 plus ln 2. Okay, this integral was not really difficult after you have changed this into an integral form from the sum. Basically, like what I wanted to share with you was the definition of Riemann sum for double integral. Yeah, and then we saw that it's symmetric. The limits of integration are all symmetric. Basically, interchanging x and y won't matter. Yeah, and yeah, that's how we solved this problem. Yeah. Basically, like if you didn't understand this, if I understand x and y, like what do I will have? Basically, this will go over here and this will go over here. Yeah, is that? No, I think that's basically what we will have is now, or now we'll again have this, and then x by y square plus x square, and then dx dy. Isn't that the thing? But now again we can interchange this. 0 to 1, 0 to 1, so problem solved. That was it. dy dx. So that was it. We solved the problem. Now there's no doubt. And yeah, hope you enjoyed the video. Thanks for watching. Look forward to seeing you in the upcoming videos too. To talk over the flow of the problem, we first invoked the Riemann sum, and then invoked the symmetry, and then used some substitution steps, and then some integration by parts and limits, and got the answer. Thanks for watching. Look forward to seeing you in the upcoming videos too.